Hello everybody, I'm Akriti Kutyala and welcome back to my channel. We are starting a new series on RCC design, reinforced cement concrete, where you will not only learn about the manual design process, but also how to model it in Revit. This series is in collaboration with Novatr, a leading platform that helps civil engineers upgrade their skills with industry-focused courses on BIM, Revit and more. Through this series, you'll gain both theoretical knowledge and practical expertise to excel in the field. So stay tuned, it's going to be an exciting journey. Today we'll continue with the series Reinforced Cement Concrete using limit state method. We'll be discussing the topic design of slabs. We'll be referring to the books by Dr. B.C. Punya and by Dr. Virender Singh. The prerequisites for the subject are IS 456-2000. I'll suggest you to have it handy with you when you are solving the questions. On this channel, we have a few membership programs. One is the Himalayan Birch, in which you can access subjects like fluid mechanics and surveying. And the other one is the Himalayan Oak, where you can access the subjects fluid mechanics, surveying, and steel structure drawing. So far in this series, we've covered the topics on design of simply supported RCC beams, simply supported RCC beam with tension bars cut off, with side face reinforcement, cantilever beams, and simply supported RCC beams with bent up bars. So in this lecture, we'll be covering one-way slab. So firstly, we'll discuss a few points based on one-way slab. So what is a one-way slab? It is a simply supported slab on wall or on beams. So we have to look at the keywords in the question. If the question says that design a simply supported slab, it means that it is a one-way slab. So this is the keyword to identify whether it is a one-way slab or a two-way slab. Then the next thing is when the slab is supported on two opposite parallel edges. For example, if this is the slab, the green one, and these are the, let's say, these supports, wall supports, which are present here. So then when the slab is supported on two opposite parallel edges, so these are two opposite parallel edges on which the slab is being supported. It spans only in one direction. So this is the direction in which the slab spans. So if we have to talk about the span of the slab, we will say that this is the span of the slab. Like in a beam, we used to consider a span. This direction will be the span of the slab, perpendicular to the supporting edges. And how did I obtain this this span? Because it is, these are the supporting edges and this span is perpendicular to the supporting edges. So this is very important when we are designing a one-way slab. If we have been provided with both the dimensions, let's say someone says that this is say let's say 5 or 7 meters, this is 5 meters. So what will be our span? Span will be 5 meters and not 7 meters. So we have to be very careful when both the dimensions of the slab is provided to us, and see that if it is supported on just two sides. Here the slab is supported on just two sides, so this will be a simply supported slab and it will be a one-way slab. The span of the slab will be in the direction perpendicular to the supports. It bends in one direction. Obviously, whenever we see that how will this slab bend, the deflection will be in this direction, not in this direction. It won't bend in this direction. Why won't it bend in this direction? Because it is being continuously supported. This is a wall right here. So it bends in one direction perpendicular to the supports. Obviously this direction is perpendicular to the supports. So now why is this important? Because in a slab we have two types of steel, two types of reinforcement which we provide. One is known as the main steel. So main steel will be provided in the direction of the span. This is very important to determine which will be the direction of the span, because the main steel will be provided in this direction. And in the other direction there will be another steel which I'm showing in purple. This will be known as distribution steel or temperature reinforcement. So the main steel has to be more and has to be provided in the direction of the span. Slab supported on all four sides. So here we saw that the slab was being supported only on two sides. So it was very easy for us to determine that if the slab is being supported on two sides, it will simply be a one-way slab. Let's say that now we have a slab which is being supported on all the four edges. So now the slab can be of two types. One, it can be a one-way slab or it can be a two-way slab. So we have to determine whether it is a one-way slab or a two-way slab. So how do we determine that? We calculate the ratio between the longer span to the shorter span and see its value. So what is the length of the longer span and what is the length of the shorter span? And if this is greater than or equal to 2, then this will be a one-way slab. So greater than equal to 2 means one-way slab, and evidently if it is less than 2, it will be a two-way slab. So here the main steel is provided in the direction of the shorter span. So main steel will be provided in the direction of the shorter span. This is very important because mostly the examiner will provide you the dimensions of the longer span and the shorter span, let's say 8 meters and 4 meters. So if the span is such that one dimension is 8 and the other one is 4, and it is clearly mentioning that the slab is supported on all the four sides, we will have to determine whether it is a one-way slab or a two-way slab. So what I can do is longer span is 8 meters, so 8 upon 4. This will be equal to 2. So because it falls within this equation, so it is a one-way slab. On the contrary, let's say this is 5. So the ratio will be 8 upon 5. 8 upon 5 will be less than 2, which means it will be a two-way slab. So whenever a slab is supported on all the four sides, we have to be very careful in determining whether it is to be designed as a one-way slab or a two-way slab. Now the main steel. Coming back to our previous one-way slab. So here the shorter dimension is 4. So the main steel will be along the shorter dimension. This will be the direction of the main steel. This yellow one is the main steel, and for temperature reinforcement or distribution reinforcement it will be along the longer span. So this is important when we are designing a one-way slab which is supported on all the four sides. So moving on to a numerical problem. This is the problem: design a simply supported RCC slab to carry a factored load of 15,000 Newton per meter square inclusive of its own weight on an effective span of 3.1 meters. Use M20 concrete and Fe415 steel. So when we look at this question, first of all, if we see that the word slab is not being supported by any prefix of one way or two way. So the examiner is not giving us the direct answer. We have to determine whether we have to design it as a one way slab or a two way slab. But like I told you, there is another keyword in this question, which is a simply supported slab. So a simply supported slab is always a one-way slab. So this is an indirect way of the examiner of telling you that this is a one-way slab. You have been provided a factored load in the form of UDL. So given one more thing which we have to note is in that in this question they have just given us one span. They are not providing us the dimensions of both the spans. They are just providing us the dimension of one main span along which we have to design. So this is 3.1 meters. We are not concerned with the dimension of this side because we can assume it to be equal to 1 meter. Always whenever we design a slab, we design it for a 1 meter width. So this is another important and easier thing which has been provided in the question. Otherwise, we would have to determine and then calculate the effective span. So here the effective span is directly provided, which is equal to 3.1 meters. The next thing given to us is M20 concrete, which means FCK is equal to 20 Newton per mm square and Fy is equal to 415 Newton per mm square. The factored load, that is WU, it is given us in the form of UDL. So small WU is 15,000 Newton per meter square. We have to be very careful if the load is factored or not. So here the load is factored and the span is effective. So L effective is 3.1 meters. Now what we do is we assume that the width for which we will be designing our slab is equal to 1 meters. That is an assumption or a standard practice which we follow while designing a slab. So we have to be very careful that for a slab we assume the width equal to 1 meter, that is 1000 millimeters. So these are the given items in the question. So the first step in this design will be assuming the dimensions. So we have already assumed the width to be equal to 1000 meters. The L effective given to us is 3.1 meters, so that is 3100 millimeters. So the thumb rule for the one-way slab, the depth of the one-way slab is D small d is equal to span upon 25. So effective depth can be assumed using this formula. So span is equal to 3100 divided by 25, which calculates to be equal to 124 millimeters. So this is the effective depth from this thumb rule. Because it is not a multiple of 10, and we generally prefer a multiple of 10 for our calculations to be easier. So we will be increasing this depth. We will not go to the lower margin, we will be going to the higher margin so that it does not fail our checks in the next step or in the upcoming steps. So we will be assuming an effective depth of 130 millimeters. Now, what we have to do is we have to calculate the overall depth. So to calculate the overall depth, we need the effective depth plus the cover, the effective cover. So now we have to assume this effective cover also. We can refer to table 16a, in which for slabs and in simply supported slabs, what we can do is we can assume a value higher than that specified here. So the minimum value is 20. So we just have to assume an effective depth greater than 20. So I'm assuming an effective depth of 30 millimeters. That makes the calculation easier. So the overall depth, capital D, is equal to 130 plus 30, which gives me an overall depth of 160 millimeters. So this is my dimension now. Width, as I told you, we will be assuming it to be equal to 1000 millimeters. So these are the dimensions. Now moving on to the next step, ultimate bending moment. So this is given by the formula mu is equal to W L effective square upon 8. So now in the question we've been provided a factored load of 15,000 Newton per meter. Because these units are in meter, we will be using the value of L effective also in the terms of meter, which is equal to 3.1 meters as given to us in the question. So substituting these values, mu is computed equal to 18019 Newton meter. However, we will be requiring this value in the units of millimeters, so we can just multiply it by 1000 to convert it into Newton millimeter. So 10 to the power 3 Newton millimeter, or I can simply write 18.019 into 10 to the power 6 Newton millimeter. So this is the maximum bending moment which will occur on the slab as per the given load. Now we have to check for the depth of the slab which we have provided. So next step is check for depth. So just like in beams, the steps almost match with a slight difference here and there in slabs. So when we check for depth, again we will be referring to annexure G, and the formula is going to be 0.36 xu max by d whole into 1 minus 0.42 xu max by d whole bracket b d square fck. Now we know that for FE 415, xu max by d is equal to 0.8. So substituting this value of 0.48 over here in this formula, we get a very simple formula for mu limiting, which is equal to 0.138 FCK BD square. So substituting these values, we have to obtain the value of D required. So this is the required depth as per the maximum bending moment which we have calculated in the previous step. So rearranging this for D will be equal to under the root of mu limiting upon 0.138 FCK B. Substituting these values, we obtain D required will be computed as 80.79 millimeters. So what value we had assumed? We had assumed a value of 130 millimeters, which is much greater than the required value of 80.79 or 81 millimeters. So this makes us safe. Hence, we can move on to the next step. This is okay. If by chance this check failed here, let's say we obtained a D required value of 131 millimeters, then we had to revise the entire thing and increase the assumed depth. So the next step is reinforcement. In this reinforcement, we will be calculating the main steel. If you remember, I just explained to you that in a slab there are two types of steel. One is the main steel and the other one is the distribution steel or temperature steel. So this particular calculation is for main steel. So again, referring to annexure G, we have the formula as mu is equal to 0.87 Fy ASTD whole into 1 minus AST Fy upon BD FCK. So now to calculate AST, what we have to do is, there are two methods. First, we'll be discussing the traditional simple method. In this, you can see that in this equation, we have AST twice. So if we open this equation or we multiply these terms, we will get AST square and AST. So substituting the values of mu, fi, b, d, f, c, k in this equation and leaving out AST. So let's substitute. We obtain this equation. Now multiplying these terms here and rearranging, we obtain the equation 0.021 AST square minus 130 AST plus 49907 is equal to 0. So we can solve this equation using the calculator or however you like and obtain the value of AST equal to 411 millimeters square and 5779.26 millimeters square. So because this value is too high for a slab, so this will be disregarded and we'll consider this value of AST, which is equal to 411.215. So we have to provide, this is the required value of area of main steel. So we have to provide a value equal to or slightly higher than this value. We cannot go lower than this value. So this is the required AST. This is one method with which you can calculate, but this is a very tedious method if you do not have a calculator. So what we do is we simply memorize a formula which is as shown on the screen. So this equation has been obtained from the equation given here in annexure G itself, but in competitive exams where we do not have the calculator, so it is easier to use this equation and calculate the value of AST. When I substitute the values in this equation, I obtain 411.06 millimeters square. So one thing which we have to be very careful while using this formula is that we have to move inwards out. Like first we will be solving this bracket. Once we are over with this bracket, we'll just minus, subtract it from 1. Then we'll be taking the under root of this, then moving outwards. So it is very tricky while solving this entire formula. So be careful so that you take into account all these brackets while substituting the values. We can see that we obtained a value of 411.06 millimeters square, which is very close to the value which we obtained from here. And in this case, we just obtained one value which is directly usable. So this is our required main steel, and we'll be moving forward with this value. So in the exam, you can use either of the equations, whichever suits you. So moving on to the next step, we have step 5 is minimum reinforcement, which will be obtained from the clause 26.5.2.1 of IS 456. The clause says that the mild steel reinforcement is in either direction in slab shall not be less than 0.15% of the total cross-sectional area. So here we have to keep in mind that it is first talking about mild steel, then it is saying that it has to be 0.15% of the total cross-sectional area. Because we are not using mild steel, let's continue reading. However, this value can be reduced to 0.12% when high-strength deformed bars or welded wire fabrics are used. So because we are using Fe415, so that is HYSD bar, so this point will be, or this part of this clause will be applicable to us. So I can simply write that AST minimum is equal to 0.12 of the total cross-sectional area. The total cross-sectional area is the width of the slab and the overall depth, and this is in percent. So to cater to that percentage, we will be dividing it by 100. So this clause translates into this formula for HYSD bars. If this was mild steel bar, then we would have simply replaced 0.12 with 0.15. So substituting the values, this calculates to be equal to 192 mm square. So the minimum area of steel which we require, which we have to provide as per clause 26.5.2.1 is 192 mm square. But what are we providing? We are providing a higher value of 411 mm square. So this is less than 411, hence we are safe. We are providing a higher value greater than the minimum reinforcement required. So now to provide this 411 AST, which we have calculated from annexure G, we need to consider clause 26.5.2.2, which specifies the maximum diameter which is permissible to be used in a slab. So the diameter of reinforcing bars shall not exceed 1/8 of the total thickness of the slab. So what it means is that the maximum diameter which we can use while uh, providing main steel is 1/8 of the total thickness of the slab. That is overall depth upon 8. So overall depth in our case is 160 divided by 8, which gives us a value of 20 mm. So the maximum diameter of the bar which we can use is 20 mm, and we have to keep the size of the bars in our slab lesser than 20 mm. Now the next clause 26.3.3 gives us the maximum distance between these bars. So for the maximum distance in these bars, we have, because this is a slab, we'll be considering the clause B of this clause, which says for slabs, the horizontal distance between parallel main reinforcement bars shall not be more than 3 times the effective depth of the solid bars, or 300 mm, whichever is smaller. So this maximum spacing has to be less than 3D or 300 mm, whichever is least. So this is the maximum spacing. Now to calculate that, I am assuming the diameter of the bar considering the above clause as 10 millimeters. So I am using a 10 millimeter diameter bars. We know that the AST required is equal to 411 millimeters square. So the number of bars that will be required for a width of 1 meter will be equal to, so to calculate that we can move in two steps. First will be equal to the number of bars. How do we calculate the number of bars? The AST required upon area of 1 bar. Area of 1 bar can be calculated through diameter of 10 millimeters. So this calculates to be equal to 411 upon diameter of one 10 mm bar. Now the spacing will be equal to width upon the number of bars, because for a slab we are assuming the width to be equal to 1000 and substituting these values, and we obtain a spacing of 191 mm. So this is the spacing which is calculated. Now, when we are providing a spacing of 191 mm, it is very difficult for the workers to provide it or the labor to provide it. So we will go to the lowest or the lower nearest multiple of 10, that is 190 mm. So this is the spacing which we are going to provide. Even if it was 195 mm or 197 mm, we would have gone with the value of 190 mm, because it is always easier to provide spacing in a multiple of 10, and it is not possible to go to the higher multiple, because then the spacing will increase than what we actually want to or are required to provide. So we will have to check this value of 190 mm with clause 26.3.3. So for 3 times of D, we calculate this value to be equal to 3 into 130, which is equal to 390. 390 mm, this value is 390 mm and 300. So the lower value, maximum spacing which is permitted is 300 mm. Our spacing which we have computed and will be providing is 190 mm, and this is lesser than 300 mm. So we are safe, because maximum spacing which was allowed was 300 mm. Therefore, we will be providing a 10 mm diameter bar at 190 mm center to center. Now before finalizing this, we have to carry out another check as per clause 26.3.2, which is simply that the minimum distance between the individual bars should be satisfied by this clause, which is simply that the diameter of the bar, the spacing should be greater than the diameter of the bar, and the spacing should be 5 mm more than the nominal maximum size of the coarse aggregate. So I can simply write. So the spacing between our bars should be greater than 10 mm or 25 mm if we are assuming a coarse aggregate of 25 mm diameter. In our case, the spacing which we have provided is 190 mm. So calculating the clear spacing will be nothing but 190 mm, that is the center to center spacing between the bars, minus the diameter of the bar. That will be the clear spacing, that is equal to 180 mm. Because 180 mm is greater than the minimum clear spacing which we require, therefore this is safe for this check, and we can move forward and simply write that provide 10 mm diameter bars at 190 mm center to center. Now there is another thing which we have to consider while providing these bars, is that the alternate bar is bent up. So whenever we are providing bars in a slab, what we do is that, let's say these are the bars which we are providing, they will be bent up. The bent up part I am showing with a dotted line here. So these, every alternate bar will be bent up. Why do we have to bend up these bars? It is simply to cater to the negative reinforcement which might be introduced, sorry, not negative reinforcement, negative bending moment which might be introduced in the bar, in the slab during the course of its life. What this simply means is that whenever we are providing positive reinforcement, or the reinforcement which we've just mentioned above, we are providing it for this type of bending, this type of bending moment. But over the supports in a continuous bar, in a continuous slab or beam or whatever element we are talking about, what happens is that there can be a reversal of load during an earthquake or any circumstance, or in general, that at the point of the support there is hogging instead of sagging. We are providing the main reinforcement for sagging between the supports. So now to cater to this hogging which occurs, or negative bending moment which occurs close to the support, we are bending up the alternate bar. When we bend up this alternate bar, what happens is that close to the support, if this is the support, close to the support, I have some reinforcement on the top side also, on the above side of the slab, which can cater to this hogging which will occur, which might occur. So to cater to this, we are providing this alternate bar bent up. So what we can write is, provide 10 mm diameter bars at 190 mm center to center, with every alternate bar bent up near the support at zero 0.1 times effective length from the center of the support. So what this means is that when we are providing these bars, we are bending up every alternate bar. While bending up these bars, we have to keep in mind a few points. So IS 456 does not specify a value to us, but there are a few practices which are being followed in the field. You can refer to different books for different practices, and every designer has his own practices. But one of the simple practice which I'm going to discuss is this one, in which we bend up the bars at zero 0.1 L, or L by 10, from the center of the support. So we consider the support from its center, we measure a value of L by 10. L here is the effective span, or I can write it simply as zero 0.1 times of L. So this is the point from which we will be bending up these bars up to and let them enter the support and provide the proper development length which we provide to other bars also. So this is for every alternate bar. Another thing which we have to keep in mind while bending up all the alternate bars is that over here in the lower, in the tension part, minimum of AST minimum should be provided. So we have to ensure that while we are bending up every alternate bar, at least AST minimum is entering our support. This value should not fall below AST minimum, or half of the or the value which we calculated in the previous uh, step. So these are a few points which we have to keep in mind while providing the main reinforcement. Next, we move on to distribution steel. Distribution steel is also known as temperature reinforcement or distribution reinforcement. So how do we provide distribution steel? It is the steel provided perpendicular to the main steel. So let's say the yellow steel which I am showing on the screen is your main steel. Then the steel provided perpendicular to this main steel will be known as distribution steel. We provide it in a slab, and the value of this distribution steel is equivalent to the minimum value of AST which we have to provide. So distribution steel, if I write AST distribution is equal to the minimum AST which is permitted to us by clause 26.5.2.1. So the formula is simple. For HYSD bars, we have AST minimum is equal to 0.12 upon 100 into B into D. So this will be the value of distribution steel which we have to provide. So let's substitute the values in this. This calculates to be equal to 192 mm square. So now we have to provide this distribution steel. Generally, we can provide a size or a diameter lower than the size which we have used for main steel, or we can use the same diameter if you want. So here we had used 10 mm diameter bars. For distribution steel, I am assuming 8 mm diameter bars. So 8 mm diameter bars can be used. Now the next challenge is to determine the spacing between these bars. So how much will be the spacing? For that, we will again refer to clause 26.3.3, and in that it tells us that the second part of this clause says that the horizontal distance between parallel reinforcement bars provided against shrinkage and temperature. So this distribution steel is actually provided against shrinkage and temperature. That is why it is also known as temperature reinforcement. Shall not be more than 5 times the effective depth of the solid slab or 450 mm, whichever is smaller. So it simply means that the maximum spacing between these bars shouldn't be less than 450 mm or 5 times D. So D is 130 mm, which calculates to be equal to 650 mm. So we have decided to use 8 mm diameter bars, and what we have to keep in mind from this clause is that the spacing between these bars should be less than 450 mm, lower of the two. So that is 450 mm. Like in the previous main steel, we calculated the spacing between the bars. We will be calculating the spacing here also. So that is simply number of bars, and number of bars will be equal to the area of the distribution steel which we have calculated equal to 192 mm square, and the area of one bar. So area of one bar is pi by 4 into 8 square. This is the number of bars. Now to calculate the spacing, we can simply use the formula width upon n. Width is 1000 meters for a slab and n is this entire value. So substituting, we get 261.799 millimeters. Again, like in the previous question, we will go to the lower multiple of 10, that is 260 mm. So we can simply say provide 8 mm diameter bars at 260 mm center to center as distribution steel. So moving on to the next step, step 7, shear. So as per clause 22.6.2, we will be considering the critical section for shear is at distance D from the face of the support. So from the face of the support, the critical section will be at distance D. So this is the clause which we are using. Now what we have to do is we have to calculate the value of shear force at this section, at the critical section, which can be simply calculated using Wu upon 2 into L. That is simply the reaction force which we will be experiencing at the support. So it will be WUL upon 2. L is the effective length. So WUL effective minus. Now if we consider that we are calculating the value of critical section, the shear force at the critical section, so R into R minus the shear force caused by this UDL. This UDL will be equal to WU into X, where X is the distance between the center of the support and the critical section. So I can write this. Now first we have to calculate the value of X. How can we calculate the value of X? If you see in this diagram, it is very simple that X is equal to width of the support divided by 2, because we are at the center of the support, plus D. Because in this question we have not been given the value of the width of the support, so we assume, and we have to write it very clearly in the exam also, we assume that width of the support is equal to 300 mm. You can assume a different value also, but this is a pretty standard value and easy for calculations. So I'm assuming 300 mm.
So x is equal to 150 plus 130 because 300 divided by 2 plus d is 130. This calculates to be equal to 280 millimeters. So x is equal to 280 millimeters. L effective, if we are using in terms of meters, that is 3.1 given to us in the question, we'll have to convert x also in terms of meters. So that will be 0.28 meters. So this is the value of x in meters. Now substituting all these values in the equation here we get, so the VU is at critical section is 19050 Newton. This is the value of shear force at the critical section. Now the next part will be to calculate the nominal shear stress using clause 40.1. So from clause 40.1 we know that the value of nominal shear stress will be equal, tau B is equal to VU BD. So this VU is at the critical section. Substituting the values, we obtain the nominal shear stress is equal to 0.1465 Newton per millimeter square. So this is the nominal shear stress. We have to check it with the maximum shear stress. For M20 concrete, the maximum tau C max, which is permissible by table 20, is 2.8. So we have to check if our nominal shear stress is less than that or not. Since tau B, that is 0.1465, is less than tau C max, that is 2.8, our value is safe and can be used for further calculation. Otherwise, we would have to redesign. Now we have to understand one thing here, that we are doing two things. One is we are bending up bars, alternate bars at a distance of 0.1 L effective from the center of the support. And the other thing which we are considering is the critical section for shear, which is at distance d from the face of the support or x distance from the center of the support. So if we are considering both these items from the center of the support, we can see that one value is x and the other value is 0.1 L effective. Now we can see that x is equal to, in numerical terms, for this question it is equal to 280 mm. So from the center of the support it is at 280 mm, and we are bending up the bar at 310 mm. So bent up bar is at 310 mm. So for the critical section, if we see here, the main reinforcement which is entering the critical section is just 50% of the steel which is being provided as the main steel, because half of the steel, every alternate bar is being bent up, so only half of the steel is entering this point. So I can simply write that at critical section, for sure, only half of the main steel is available. So if I write AST at critical section, it will be AST main. For this particular question, this is there. So you have to check for every question whether the critical section is beyond the bent up point or before it. So AST main upon 2. Our AST main was equal to 411 mm square. So divided by 2, this calculates approximately equal to 206 mm square. So for the critical section at for shear, the AST available is half, which is equal to 206 mm square. This is important because now we are going to calculate the percentage of steel present at critical section using table 19. So we have used this table before. So from table 19, we know that P, percentage of steel, is equal to AST upon BD into 100. And because this is being calculated for shear, so this will be at the critical section for shear. So substituting the values, we have 206 upon 1000 into 130, and in the numerator we have another 100. So this percentage computes to be equal to 0.158%. So just for the sake of ease, I am increasing it or rounding it up to 0.16%. Now for this value, we can see that it lies between 0.5 and 0.25. So for M20, we have values 0.28 and 0.36. So we will have to interpolate it and find the percentage of steel corresponding to 0.16%. So calculating that, we prepared the equation and calculate the tau c is equal to 0.29 Newton per mm square. So this is the value of the shear resistance provided by, or shear strength provided by, concrete for a percentage of steel corresponding to 0.16%. Now generally in beams we stop at this step and move on to the next, but here we have another clause to be considered because what we are designing is a solid slab. So for solid slabs, as per annexure B, we have to consider this table given by clause B 5.2.1.1, which says that for solid slabs the permissible shear stress in concrete shall be K times the tau c value. We have calculated the tau c value equal to 0.29 Newton per mm square. Tau c dash, that is the value which we are going to use, will be equal to K times tau c. Tau c we know from table 19, K will be obtained from this table. So what do we have to do? Overall depth of the slab is given to us. For us, the overall depth of the slab is 160 mm. So this lies somewhere between 175 and 150. So the value of K will be between 1.25 to 1.3. So again we have to interpolate this value. So on interpolation we obtain the value of K equal to 1.28, which is correct because the value had to lie somewhere between 1.25 and 1.3. So now tau c dash is equal to K into tau c, which is equal to 1.28 into 0.29. This calculates to be equal to 0.37 Newton per mm square. So this is the value of shear strength of concrete which we are going to use for a slab in this particular question. Now we have to compare this value with tau v. Tau v we had calculated equal to 0.1465 Newton per mm square. So because of the load, the shear which the slab is going to experience is 0.1465 Newton per mm square, and the shear strength of concrete is 0.37 Newton per mm square. Hence, tau v is less than tau c dash. Therefore, the uh, slab is safe for shear and no shear reinforcement is required. So no, if you see, we hardly see any stirrups or any sort of shear reinforcement in a slab practically, because mostly the slabs come out to be safe in case of shear. If it is not safe, then we will have to redesign, because we don't provide any stirrups in a slab. So this shows that up till now the design is going to be right. Next is check for deflection. For deflection, again we have to calculate the percentage of steel, but this will be at the center of the span. So center of the span means that we have to consider the AST which we have provided. So AST provided at the center of the span is 10 mm diameter bars at 190 mm center to center. So we will be calculating this AST provided again for a width of 1 meter or 1000 millimeters. So we can simply calculate AST provided as the the area of one bar into total width is B divided by the spacing between these bars. So this calculates to be equal to 413.36 millimeter square. So this much area of steel we have provided. So P calculates to be equal to 413.36 divided by 1000 into 130 into 100. So this is equal to 0.3179%. Now we've calculated P. We know from previous questions Fs can be calculated by 0.58 Fy into AST required divided by AST provided, again at the center of the span. We know that we have a requirement of 411, but we have provided a steel of 413 millimeter square. So this calculates to be equal to Fs is equal to 239.325 millimeter, Newton per millimeter square. Now from the following figure, that is figure 4, we can calculate the modification factor for tension reinforcement, that is KT, which we consider. So KT can be simply calculated using this figure. let's say we have the percentage of steel equivalent to 0.3, because this will make it easier. So 0.3 will fall somewhere here. This is 0.3, and the Fs value is 239.325. We are approximating it to be equal to 240, slightly higher than what we have calculated, because this is a very approximate graph and we have a direct value of 240 here. So this is the value of 240 on this curve. So we can assume that this value kt is equal to approximately 1.65, because this will be 1.67 here somewhere. 1.7. This will be 1.8. So we are falling somewhere between 1.7 and 1.6. So I'm assuming the value of kt to be equal to 1.65. Now we know from previous questions that this is a simply supported flexural member and the basic value of span is less than 10 meters. So the factor which we are going to use is will be equal to 20. So the factor is 20 into kt into kc into kf, where kt is modification factor due to tension, kc is modification factor due to compression, and kf is modification factor due to flange of the beam. So because the cross section here is rectangular, so kf is equal to 1. We are not experiencing any compression force here. So again kc is equal to 1, and kt we have obtained from figure 4 in the previous slide. So we can substitute the values and obtain 20 into 1.65 into 1 into 1. So this calculates to be equal to 33. Now from the provided values, L upon D provided is equal to the effective length upon the effective depth, which is equal to 3100 upon 130, which calculates to be equal to 23.8. So this value is less than the maximum permissible value of 33. Hence the slab is safe in deflection. So now moving on to the detailing, we can see that the main steel has been provided at the bottom. This you can see is written as 10 millimeter at diameter at 190 mm center to center. So this is the main steel which is provided at the bottom of the slab. Then on the top of the main steel, we provide the distribution steel, which I am showing you in green over here. So if this is the main steel, the green one is the distribution steel. So this is how we provide main steel and distribution steel. So if you see, the distribution steel is shown as 8 mm diameter at 260 mm center to center, which we have calculated in the question. Again, the main steel is being bent up, alternate bar is being bent up, and even the distribution steel is bent up. So at what position do we bend it up? We bend it up at 0.1 L from the center of the support. In some books you will find these practices to vary slightly, so just stick to one practice, whichever is comfortable for you. Then we have the width of the support, which we had assumed is 300 mm. This is the calculation for the clear span. We do not require to calculate it. We can simply make another arrow and write this is the effective span of 3.1 meters, which is given to us in the question. Now we have to also show it in the plan. Now when we show it in the plan, you can see that this bar is completely solid till here, and then at 0.1 L from the center of the support we are showing a dotted line. This dotted line means that this bar has been bent up from this end. So keep in mind, if a bar is being bent up from one end, it will not be bent up from the other end. So alternate bar, here we are bending up the alternate bar. The second bar is bent up from here and it will remain as a solid bar on this side. So this is the practice which is being followed in the particular question, and this is the basic detailing. The depth of the bar is the slab is 160 mm. In this lecture, we covered the design of a simply supported RCC slab, or we can simply say a one-way RCC slab. Thank you. I hope you liked the video. Like, share, and subscribe, and join the membership program. Thank you.
Alright, so this is our design is. Let's just model this in Revit. As you can see that this time we have a little tougher reinforcement shape. So let's just model it in Revit. So as you can see that I have already modeled columns, our beam is resting on it. So this is my plan view. I have cut the section to navigate through the different views, and it will be easy for to place the reinforcement. As you can see, I already added one, so I'll show you how I added it. So first of all, go to structure, cover, select the element for which you are providing the cover, and just add your cover. After that, rebar, let's see the requirement. So as here we want this A and B, right? So that is 10 mm, 190 mm center to center. So but instead of set we will go with single, because we will be changing the shape like this, right? So single will work, and then we can copy it. So as you can see that okay, this is shape and I have added it, right? Now I'll go to the elevation, right? I'll just double click to edit, and here it is asking that it should be away from the column 310 mm. So how I'll do it, I'll just place one line here. Let's make it 310, and same way I'll just mirror it, right? And we'll check the distance here as well. But right now this side is not required. I'll just copy and rotate it. So let's focus first here. So after this, I'll just make it in a shape, right? I think this is the appropriate shape. Trim command, just trim it and delete the line, because it was just for the reference, right? So yeah, after doing it, you can see the shape, right? The same way this will be the reverse, right? So I can do one thing. So instead of I'll just delete this one, I'll just copy this. I'll go to the same section, I'll just mirror it, and then I'll just go to the I'll just mirror it. I'll just rotate it, right? After copying it, rotate, just make it 180, right? Okay, in case it came out, just go to the section view, and no, I think it's all good. So you can see that if we go to the see, this is how it is done, right? And as you can see, the pattern is like this, BA. So what I'll do, I'll go to the plan view, I'll just copy it here, and this one I'll copy here, and after that I can just equal it. So after doing it, I'll just okay, if that does not work, you can just simply check the distance. So just check what is the distance. 109, 106, 69. So you can do one thing, section view, right? So just just delete this too. Okay, go to the structure, take the command again, okay, and get shift a little here, move it, right? Now it's fine. So after that, take the command again, and you can simply go with the rebar set, fix number 4, just place it. Okay, for now copy this to this, right? And this is not this one. Okay. This is what you have. Yeah. You can just select this, right? And delete and just select copy. And just place it and then see the distance between 88. So it should also be 88. It's 102. So just select it and make it 88. Yeah, and now it's all equally distanced. Go to the 3D view, and yeah, this is how it will look like. So this part is done, AB. Now it's time to place this 8 mm 260 mm center to center. For that you have to open this section, yeah, right, this one, and structure reinforcement typical shape, and that will be of 8 mm, right? So I'll just create a new type of 8 mm. So I'll just make this 8. Right, and after that I'll just go to the rebar set with the maximum spacing of 260, right, and just place it, and then you can just move it, right? Yeah, so after that, okay, you can edit it this way, and yeah, it's done. So let me just move a bit. 3D, yeah, and this is how you can see that you can place. The similar way you can go to this view. Okay, just copy this, just extend it, right? Okay, copy this to upper side and just edit. So click, okay, here custom, edit, select the unnecessary ones, okay, this as well, and just remove. Okay, so of course Control Z. Yeah, so just you have to delete this, remove bars, and you can shift this to so if in this case what you can do, edit this bar, just make it here, so yeah, trim, right, or else like this, trim it, and yeah, it's done. That's how you can just, yeah, right, that's how we can just place it. The same way this as well, or else you can just copy the previous one, whatever suits you. Yeah, so yes, this is how you can just model rebars. Okay, simply amazing and very easy in Revit. Yeah, so yeah, thanks for watching.